So we have studied about electric charges in the unit 1, and we know that if a charge is at rest, it will produce an electric field around it. And in unit 2, we have learned about electric current. We know that if charges they move inside a conductor, then that charge which is in motion inside a conductor will constitute a current. Now, in the unit 3, we shall learn about the magnetic effects of current and magnetism. Now, in this unit 3, we have two chapters, chapter 4 and chapter 5. Chapter 4 is moving charges and magnetism. In this chapter, we shall learn about the concept of magnetic field and or state experiment. Now we shall also do another activity to demonstrate the magnetic effects of current. And we shall learn two laws, which is called Biot-Savart Law and Amperes Law. These laws can be used to find the magnitude of the magnetic field at any point due to a current carrying conductor. So in this lecture, we shall cover these two laws. Okay, so we shall start with the concept of magnetic field. Now, the space around a current carrying conductor in which its magnetic effect can be experienced is called a magnetic field. Now, to demonstrate this concept of magnetic field, we will consider an activity. So here we have an iron nail. And here we have a copper wire which is wounded around an iron nail. Now, if I bring this nail towards the other nail, you can see there's no effect. But here, if I bring a battery and connect the positive end of the battery to one end of the wire and the negative end to the other end of the wire, then as I do this, current will flow through the wire. And if I bring this close to this nail, you can see that the other nail is attracted towards the nail which is wounded by the copper wire. So this is the magnetic effect of current. Okay, if current flows through a conductor, which is the copper wire, then it produces a magnetic field around it, so that the magnetic effects of the current can be experienced. In this case, the nail is attracted towards the other nail which is wounded by the copper wire. So this behaves as a magnet. Okay, so this copper wire which is wounded around the nail behave as a magnet. Now if I disconnect this, let's just see what happened. So if I disconnect it, you can see that the nail is no longer attracted towards the other nail. This is because there's no current flowing in the copper wire. So if there's no current, there's no magnetic field. Hence, there's no magnetic effects of this current. So this nail will not be attracted towards the other nail. So even if I bring it close, you can see here, it does not have any attraction. Only if there is current flowing in the copper wire, there is an attraction. The nail will be attracted towards the other one. So we have seen the magnetic effects of current. Now I will tell you about Ørsted's experiment. In the 1820, a Danish scientist named Ørsted discovered the magnetic effect of electric current. So Ørsted found that when a wire AB carrying current was held over a magnetic needle NS, such that electric current passed from the end A of the wire to the end B, which is shown in figure, the north pole of the needle got deflected towards west, that is into the paper. And on holding the wire below the magnetic needle, the north pole of the needle got deflected in the opposite direction. So this indicated that magnetic lines of force below and above the needle are directed in the opposite directions. So thus Oersted experiment led to the discovery that when the electric current passes through a conductor, magnetic field is produced around it. So that is Oersted experiment. So Oersted is a scientist which discovered this magnetic effect of current. And as you have seen in the early activity, when current is passed through the copper wire, then that copper wire wounded around the iron nail behave as a magnet. Now to find the magnetic field, the strength of the magnetic field around a current carrying conductor, we will make use of two laws. One is Biot-Savart's law and the other one is Ampere Circuital Law. Now Biot-Savart's law states that the magnetic field produced due to a small conductor of length dl carrying current I at a point at a distance r is given by dB is equal to k IDL sine theta divided by r square. Now this k is a constant of proportionality. Theta is the angle between the direction of current and the line joining the conductor to the point in which we want to measure the magnetic field. And I is the current, dl is the small portion of the conductor, and r is the distance of the point in which we measure the magnetic field from the small portion dl. Now we consider this diagram below. Here we have a conductor xy and current I is flowing in the conductor xy. And here we have AB is the small element or the small portion of the wire, that is dl. So AB is equal to dl. And here P is a point in which the magnetic field due to the current flowing through this small portion dl is to be measured. And theta is the angle between the line CP and the direction of flow of current. Now this IDL here, this is known as a current element. Okay, this is defined as a current element. It is a vector quantity. IDL vector is a vector quantity and it is in the direction of flow of current. Now don't be confused. Here you'll have to take both the current and the length dl to be the current element. Okay, not just dl, not just the current, but both I dl is known to be the current element, and it is a vector quantity in the direction of the flow of current. So here we have r, the distance of the point P from the current element IDL, and r cap is the unit vector in the direction from C to P. So according to Biot-Savart's law, the magnetic field at point P is given as k IDL sine theta divided by r square. Now this is just the magnitude, where your k here is equal to, in SI unit, is equal to mu naught by 4 pi, and this is equal to 10 to the power minus 7 Tesla per ampere meter. Now Tesla is the unit of magnetic field, and here mu naught is called absolute permeability of vacuum. Now in the electric field we have the absolute permittivity, but while studying the magnetic field we have the absolute permeability. And therefore in SI, Biot-Savart law can be expressed as dB is equal to mu naught by 4 pi IDL sine theta divided by r square. And this magnetic field is actually a vector quantity, so its direction can be known. And to know the direction of the magnetic field, we'll have to express Biot-Savart's law in the vector form. That is, in vector form, your Biot-Savart's law is expressed as dB vector, which is equal to mu naught by 4 pi IDL vector cross r cap divided by r square. So here I told you that IDL vector, this is a current element, is called the current element, and it is a vector quantity in the direction of flow of current. And r cap here is a unit vector. Okay, it's always directed away from the current element. So here in the diagram, your r cap is along CP, that is from C to P. So here we can also write this Biot-Savart's law in vector form in a different way. That is, dB is equal to mu naught by 4 pi IDL vector cross R vector divided by R cube. Now why we write R vector here? Because we know that R vector is equal to R cap. Okay, now simply R is the magnitude of the R vector and R cap is the direction. So if we put the value of R cap from this formula, R cap is equal to R vector divided by R. So instead of R cap, we put R vector divided by R. Hence we get this IDL vector cross R vector divided by R cap. So now after expressing this Biot-Savart's law in vector form, you can find the direction using the right hand vector product rule. So in the right hand vector product rule, your fingers represent the direction of the current element. Okay, all the fingers represent the direction of the current element. And as you close the fingers towards the R vector or the R cap, then you extend the thumb. And this thumb will actually give you the direction of the magnetic field. So in the figure, you put your fingers along the XY, then you close your fingers towards R cap. And as you close your fingers towards R cap, you extend your thumb. And in the figure, the direction of the magnetic field is perpendicular to the plane and is directed towards the paper. It's directed inwards, okay, towards the paper. So if the current flows in the opposite direction, that is from Y to X, then again you put your fingers, all your fingers, then you close your fingers towards R and extend the thumb. Then you'll get the direction of the magnetic field, which is outwards and perpendicular to the plane of the paper. So that is how you find the direction of the magnetic field. So the above formula dB gives us the magnetic field due to a small current element. But to find the magnetic field due to the whole conductor xy, then you'll have to integrate dB over the whole length. Hence the magnetic field due to the whole conductor xy is given as B vector, and this is integration of dB. So we'll get mu naught by 4 pi integration IDL vector cross r cap divided by r square. So this is the magnetic field due to the whole conductor at the point P. So now we'll apply this Biot-Savart's law to find the magnetic field due to a current loop. So here we consider a circular loop of radius A, center O, and carrying a current I as shown in the figure. Now the plane of the loop, that is the YZ plane, is perpendicular to the plane of the paper, while the axis of the loop, that is OX or x-axis, lies in the plane of the paper. Now let P be the point on the axis of the loop at a distance OP, which is equal to x from its center. Now where the magnetic field due to the circular loop has to be determined. So we'll have to determine the magnetic field at point P. Now in order to do that, we'll have to consider a very small portion of the wire AB of length DL. Okay, so we consider AB, the small portion of the loop, and is equal to DL. Then we join the point P to the middle point C of the portion AB. And suppose this CP is equal to R. So here in the diagram, we can see that the angled BCP or the angle ACP, this is equal to 90 degree. So applying Biot-Savart's law, the magnetic field at point P due to the current element at AB is given by dB is equal to dB vector is equal to mu naught by 4 pi IDL vector cross r cap divided by r square. Now here IDL vector, I told you this is a current element. It is a vector quantity in the direction of flow of current through AB, and r cap is a unit vector along the line CP. Now the magnetic field due to the small current element at point P points in the direction of the vector IDL cross r vector, and this dB vector has been shown in the diagram and is represented by the PL vector. And since the angle between IDL and R cap is 90 degree, the magnitude of dB vector is given by dB is equal to mu naught by 4 pi IDL divided by r square. So here remember IDL cross r cap, this is a vector product. It is equal to IDL r sine theta. Theta is equal to 90 degree in this case. Hence we have dB to be equal to mu naught by 4 pi IDL sine 90, which is equal to 1. Therefore IDL divided by r square. So that is the magnetic field at point P due to the current element at AB. Now we consider another current element AB dash, which is diametrically opposite to that of AB. And here the magnetic field at point P due to this current element at AB dash is represented by dB dash. And in magnitude, the magnetic field dB dash is equal to the magnetic field dB, but the direction is different. And as you can see in the diagram, the direction is represented by the PM vector. So we have two magnetic field dB and dB dash. Now we'll have to resolve these two into two components, the cosine and the sine component. And as you can see in the diagram, dB, the component of this dB vector, one is along the z-axis and another one is along the x-axis. So the one along the z-axis is dB cos theta, and the one along the sine x-axis is dB sine theta. Similarly for dB dash also, the component along the z-axis is dB cos theta, and that along x-axis is dB sine theta. So remember dB dash and dB is equal, hence we write this component of dB dash to be dB cos theta and dB sine theta. And since dB cos theta, the cosine component is opposite to one another and they are equal in magnitude, therefore they cancel the effect of one another. And since dB sine theta is in the same direction, these component along the px axis will contribute to the magnetic field due to the whole loop at this point P. Hence the effective component of the magnetic field due to the current element is just that of the sine component, that is dB sine theta. And if we want to find the magnetic field of the whole circular loop, we'll have to integrate dB sine theta over the circumference of the loop. Therefore, the magnetic field at point P due to the whole circular loop is integration dB sine theta. B is equal to integration over the circular loop dB sine theta. And putting the value of dB, we have integration over the closed loop mu naught by 4 pi I dl by r square sine theta, then mu naught by 4 pi I r square sine theta is taken common, outside of the integration, so we have integration of dl only, and integration of dl, if you add all the dl, you'll get the circumference of the loop of radius a. Hence we have integration dl to be equal to 2 pi a. Hence the magnetic field at point P due to the circular loop is given as B is equal to mu naught by 4 pi I divided by r square sine theta 2 pi a, or this is equal to mu naught by 4 pi 2 pi a, or 2 pi I a divided by r square sine theta. Now sine theta, again we consider this triangle the OPC. So if you consider the diagram and the triangle OPC there, now OPC, in a triangle OPC, sine theta is equal to perpendicular, which is A, then divided by hypotenuse, which is R. So we have sine theta to be equal to A divided by R. And putting this in the above equation, we will get B to be equal to mu naught by 4 pi 2 pi IA divided by R square into AR, and that will be equal to mu naught by 4 pi 2 pi I A square divided by R cube. And since R, again from the triangle the OPC, your R is the hypotenuse, so the hypotenuse is given to be root over the square of A plus the square of X. So R is equal to square root A square plus X square. Hence, the final expression will be B is equal to mu naught by 4 pi 2 pi I A square divided by A square plus X square to the power 3 by 2. So this is the expression for the magnetic field due to the current loop at the point P, which is at a distance x from the center of the loop. Now if the loop has n number of turns, then the B will be equal to mu naught by 4 pi 2 pi n I A square divided by A square plus X square to the power 3 by 2. And suppose if P lies on the center of the loop, that is your X will be equal to 0. So putting X to be equal to 0 in the equation, we'll get B to be equal to mu naught by 4 pi 2 pi I divided by A. So this will give us the magnetic field at the center of the loop. And if the loop have n number of turns, then the magnetic field is B is equal to mu naught by 4 pi 2 pi Ni divided by A. Now we come to another law, which is Amperes Circuital Law. Now this law is similar to this Gauss law in the chapter 1. In Gauss law, remember, we'll have to enclose the charge distribution or the charge by using a closed surface. Now in this Ampere Circuital Law, we'll have to enclose the current carrying conductor with a loop. Okay, not with a surface, but with a closed loop. So this Ampere Circuital Law, it states that the line integral of the magnetic field B around any closed path is equal to mu naught times the total current I enclosed by that path. That is line integral B dot dl is equal to mu naught I. And here you can see that in the Gauss law we have surface integral E dot ds. Here we have line integral B dot dl. And this is equal to mu naught I. In the Gauss law, we have instead of I, we have charge, and instead of mu naught, we have 1 by epsilon naught. So this is the law which we use in the this magnetic field, in finding the magnetic field. So here, Ampere Circular Law, we have in line integral b dot dl is equal to mu naught I. Now, to understand this Ampere Circuital Law, let us apply this law in finding the magnetic field due to a straight current carrying conductor. So here we have a straight current carrying conductor, which is xy, and the current I is flowing through this long conductor xy. And the magnetic field at point P at distance r from the conductor can be found out by using this Ampere's Circuital Law. So to use Ampere's Circuital Law, again we have to enclose this current carrying conductor by a closed loop. In this case, we choose a circle of radius r as the closed path or the closed loop. Then according to Ampere's law, we have line integral b dot dl is equal to mu naught I. Now we evaluate first this line integral. So here line integral b dot dl is equal to b dl cos of 0 degree. Now 0 degree, because if we look at the diagram, we see that the magnetic field B is in the same direction as the small length dl. So here the angle between B and dl, this is 0 degree. Therefore we have this BDL cos 0 degree, and cos of 0 is equal to 1. Therefore this is equal to B, which is taken outside of the integration. We have integration of dl, then again integration of this dl, the small length dl. If you integrate this, you'll get the circumference of the circle, which is 2 pi r. Hence the line integral to b dot dl over the closed path is equal to b 2 pi r. Hence putting this in Ampere's Circuital Law, we have b 2 pi r is to be equal to mu naught I. Hence B is equal to mu naught I by 2 pi r. So this is the magnetic field due to a straight current carrying conductor at a point P, which is at a distance r from the straight current carrying conductor. So that is one application of Ampere's Circuital Law. Another application of Ampere's Circuital Law is to find the magnetic field due to a solenoid and a toroid. Okay, a straight solenoid and a toroidal solenoid. But according to the revised syllabus, the derivation is not required. So here I'll just tell you what is solenoid and what is the magnetic field of the solenoid. So a solenoid is a long coil of wire consisting of closely packed loops such that its length is very large as compared to its diameter. So this is one point to be noted here. The difference between a coil carrying current of n turns and a solenoid is that the diameter of the solenoid is very, very small as compared to its length. So in the earlier section, in the activity shown in the beginning of the video, you can see that the length of that coil is very, very large as compared to the diameter of that coil. So that is an example of a solenoid. And here in the diagram also we have a solenoid in which we have A in between, and say L is the length of the solenoid. So here I is the current flowing through the solenoid of length L, and here we have defined a term n, small n, to be the number of turns per unit length. That is, n is equal to number of turns of the solenoid divided by the length of the solenoid, so that the magnetic field inside the solenoid is given as mu naught n I, where mu naught is the absolute permeability in free space. So this is the formula for the magnetic field inside the solenoid when there is air in it. And if the solenoid has a core of material having relative permeability mu r, then the B will be equal to mu naught mu r and I. Okay, or B is equal to mu and I, where mu is the absolute permeability of the material of the core. So if you have an iron nail inside that solenoid, then the magnetic field of that solenoid will be given by this formula. B is equal to mu and I. And as you can see here, it depends upon the number of turns per unit length and the current flowing in the solenoid. So more is the number of turns per unit length, more is the magnetic field, and more is the current flowing in the solenoid, more will be the magnetic field inside the solenoid. So if you want to make a solenoid of a large magnetic field, you have to closely pack the coils together. Okay, so you wound the coil around an iron nail and you closely pack that coil together so that the number of turns per unit length will be large. Now the magnetic field due to a toroidal solenoid also is same as that of a straight solenoid. So here a toroidal solenoid is actually an anchor ring or a torus around which a large number of turns of metallic wire are wound. So the diagram of this toroidal solenoid is shown in the figure, and the magnetic field inside the toroidal solenoid is given to be B is equal to mu naught I, which is same as that of a straight solenoid.